So, what we will start from today, and this is what we will end with the course, is some spectroscopic tools. You know what is spectroscopy, a little bit of that, and absorption, fluorescence, IR, CD. Okay. So, that is why this class starts with this heading experimental tools. That means, the tools you would need, these are not the techniques, these are the tools you would need to probe the folding and unfolding of proteins. Right. But remember, these tools are very general, because we are talking about, because this is a course on biophysical chemistry, our focus is mainly on proteins or biomacromolecules or biomolecules. But as such, you take any other compound or molecule which is not a biomolecule, still these tools would be equally applicable, right. So, that is the real good thing about the generality of this thing or this subject called spectroscopy. So, this you have seen before, but I will just quickly scan through it. So, some of these experimental techniques, one is fluorescence. Look at the relevant time scale, you can go from nanoseconds to seconds, right. And what do you get out from it? So, if fluorescence is, as says, under intrinsic means something which is present in the protein itself. So, some of the intrinsic amino acids are tryptophan, tyrosine, also phenylalanine, but tryp and tyrosine are the ones which are mainly used in the fluorescence emission of. Then ANS, I told you before that ANS is a certain dye called 1-anilino-8-naphthalene sulfonic acid. Now, this dye is commonly used to look at exposure of hydrophobic patches in proteins. Okay. So, you can also look at the change in fluorescence intensity of ANS to figure out what is going on as you change conditions. Then third is FRET. You know, we have talked about this a little bit. FRET is about how the transfer of energy occurs between a donor and acceptor, and this depends upon the distance between these two, right. So, you can understand, if you are looking at a conformational transition, you start from an unfolded state and you come to a folded state, and you have two chromophores, this donor acceptor. What will happen is, in unfolded state they would be really far off. So, fluorescence or rather energy transfer efficiency would be really low. When they come very close to each other, the energy transfer efficiency would be really high, and that is how you can track it, and you can even use it for kinetics, right. And then there is something known as anisotropy. If you remember this thing, we had done this protein apomyoglobin. Did you remember apomyoglobin, when we were talking about this ribosomal tunnel, and we said that apomyoglobin starts getting some structure, and there was something known as rotational correlation time or rotational spectroscopy, where you would look at the rotation of apomyoglobin fragment and see whether it is bound to the peptide tunnel or not. So, that is essentially what it is, anisotropy. So, these are some of the main techniques that fall under fluorescence. Then a very important technique called circular dichroism. So, for example, if you get a protein, right, if you get a protein and the first thing someone asks you, does it have a structure? If it does have a structure, what structure does it have? I am talking about the secondary structure. So, then immediately what you can do is, you can take the sample, put it in the CD spectrometer and take our Acura spectrum, right, and that is one of the easiest ways of finding out whether a protein has an alpha helical structure or a beta sheet structure or a mixed type. You know, you can do fittings and all these things. Not only the secondary structure, you can also look at the tertiary structure. So, that is why you will see there are two regions, wavelength regions, one is the far UV and one is the near UV. So, what is this far and near about? Near and far is with respect to what? Why do we call near, why do we call far? What wavelength? Visible, right. So, if anything is near UV, that means this is in the UV region, but near to the visible. So, visible say is from say 400 to 700 nanometers, right. So, anything which is close to 400 would be near UV, because it is near to the visible region. The farther you move lower from 400, you go to the far UV. So, typically for CD, the far UV looks at secondary structure, that is what it says. You can see the far UV is secondary structure. So, that is alpha helix, beta sheet and all these things, right, even random coil. The near UV looks at the tertiary structure. Okay. So, there will also be tertiary structural changes which happen in the near UV region. So, near UV region would, as you see, 350, 400 and all these things. Okay. So, then there is something known as small angle X-ray scattering. So, small angle X-ray scattering, popularly known as SAXS. Now, what does it tell you? It gives you the dimension and shape of the polypeptide chain. Now, this is what you need it for. Say for example, suppose you are unfolding a protein, right, that means you are destroying the structure in a protein, it goes from folded to a native to a non-native or denatured state. Now, someone asks you what is the change in the dimension. Now, you know that if you are going to open a protein now, the dimension is going to change, because you are disrupting forces and the protein is now slowly opening up. Now, all proteins would not open up exactly the same manner. Some proteins might undergo a huge change in dimension, some proteins might not be undergoing that much of a change in dimension, but how would you know what is happening? So, one of the techniques is small angle extracting, which tells you or gives an idea about the approximate dimension of your protein state, whether it is in the unfolded or whether it is in the folded. And remember, whenever you are talking about this SAXS, you are doing in solution. So, you always look at what? You always essentially look at the hydrodynamic radius, right, because you always have water molecules associated with these things. Okay, the next one is FTIR, it is called Fourier transform infrared. Now, I know that in one of your physical chemistry practicals, you have done this infrared spectroscopy. What was that experiment? Was it this, wasn't it a dimer formation or something like that you did? It was in your first practical. You use the IR instrument, right, in an instrumentation lab. So, that is the principle. Proteins have remember when we were talking about the laser induced temperature jump, we talked about this IR absorption band 1631 for an alpha helix. So, this is essentially what you are talking about. So, if you take FTIR, then you would be getting that information of your secondary structure as well. Now, what is the time scale for this? The time scale is nanoseconds to seconds. So, then the other one is something which you know very well, it is called absorbance. This is essentially Lambert-Beer's law, right. Absorbance in the UV visible region. FTIR was absorbance in the what? IR region, because you are looking at bond stretching, bond vibration. This is your electronic transition, you are looking at absorbance in the near UV. So, it is nanoseconds to second, that is the time scale, it can even go lower. What essentially look at is aromatic residues or cofactors. Okay. So, for example, cofactor, how do we define a cofactor? Well, let us take this myoglobin, right, or hemoglobin. Hemoglobin has what? There is a heme prosthetic group in the middle. So, this one has a characteristic transition. Do you know what the transition is known as, or that band is known as? Pi to yes, pi to pi transition. What is the band known as? Starts with an S. It's called a Sorey band. So, the Sorey band is something which you can look at the absorbance of and see what changes are going on at some structural level, right. Then obviously, of NMR, there are two types, one is real time, one is dynamic. So, you can look at the the breadth of time scale. In one case it is millisecond to second, in the other case it is about 200 microseconds or so. Okay. So, that is pretty much about the common tools or the tools that are used commonly when people are looking at proteins or investigating proteins, no matter for what reason, right. But before we go into spectroscopy, we have to know some very basic things, right. So, let us look at this. The first basic thing obviously is, if you are interested in spectroscopy, I do not know how much was covered in group theory and spectroscopy in your class, but that was mostly from the group theory point of view. But if you would be ever interested in spectroscopy, if you are interested in spectroscopy, if you want to take spectroscopy up as your future PhD project or whatever, then please do look up time dependent perturbation theory if you are not taught, okay, at any subsequent time of this. So, time dependent perturbation theory we cannot go over in this class, because it would take some time and we do not have much time left. So, time dependent perturbation theory is the thing which from where essentially spectroscopy originates. Remember, perturbation is a certain perturbation. What you are, in this case, if you are doing spectroscopy, what are you perturbing the system with? You are perturbing the system with your electromagnetic field, which is a radiation, and that is why that comes into your perturbation. Okay, it is like H0 plus lambda H prime. Do you remember? That was your perturbation theory. That H prime is an oscillating function of your, it is essentially a radiation, okay, oscillation function of time. So, please look that up. So, that is extremely essential. But what we will do is, we will consider the fact that okay, time dependent perturbation theory is there, we have to look that up. We will move forward and we will talk about something which is very fundamental. This is referred to as Einstein's coefficients. So, referred to as Einstein's coefficients. Okay. Now, let us consider this two level system. Okay. So, two level means I have a 2 level system, that means this is my ground state, G stands for ground, and this is my excited state, E stands for excited. Okay. Now, what I will do is I will throw in some radiation, that is some energy density. The system, whatever system I am looking at, would absorb that and then move from the ground state to the excited state. So, the first process is absorption. Okay. So, the first process is absorption. So, this is absorption. Okay. So, here after you have excited the molecule from the ground state to the excited state, what will happen? The molecule cannot stay at the excited state for infinite time. What it would try to do is it would try to come down to the ground state. Now, okay, it can come down to the ground state in 2 ways. What I mean by 2 ways? One is it can just spontaneously by itself come down, right, spontaneously by itself come down. That means, let me give you a wiggly line. So, this is referred to as a spontaneous downward transition, okay, from the excited state to the ground state. Okay. The other one is, if one is spontaneous, what is the other way of coming down? Can you tell me? Yeah, what does it give rise to? That is what happens in lasers, right. What is the full form of laser? Right. So, if this is spontaneous, then what is the other form? Yes. If it is spontaneous, the other one is non spontaneous, right. Very good. What you just said, Pancham, what is that? Light amplification by stimulated emission. That means, okay, good, understood. So, if one is spontaneous, that means it just comes down by itself, it does not have to be told to come down to the ground state. The other one is stimulated, that means there is something which stimulates its transition from the upper level, which is the excited state, to the ground state, right. So, then this is the other one we have. So, this is your stimulated emission. Okay, this is stimulated. One is a spontaneous transition, one is a stimulated transition. Now, stimulated emission of radiation, as was pointed out, is the principle of laser, right, light amplification by stimulated emission of radiation, right. But remember, these are 3 distinct processes. Okay. But also try to realize one thing, when you are coming down, you can have 2 types of transitions, right, spontaneous and stimulated. But when you are going to have an absorption, are you going to have any spontaneous absorption? You are not going to have a spontaneous absorption. Why? Because for absorption you need to supply energy, right, and only after it absorbs the energy would it go to the excited state. There is no way you can just go like that, right. It just cannot happen that it was sitting on its chair one fine day and then suddenly it jumps to the excited state. It cannot do that. It has to be hit with a certain electromagnetic radiation which it would absorb, right. Okay. So, that is why there are 3 exclusive processes, okay, in very general terms. Now, what I can do is I can say that, okay, let us try to write some equations down. How do we do that? What I say is, based on this, I say that my rate of transition from the ground state to the excited state, where 1 refers to the ground state and 2 refers to the excited state. Okay. So, that means 1 is the ground state and 2 is the excited state. Okay. So, this is equal to, that means I am looking at the rate of transition, well W12 is the rate of transition from the ground state to the excited state. It would depend upon what? Now, think about a rate in your chemical reaction. What does it depend upon? It depends upon rate constant, it depends upon a concentration. Very good. So, now in this case instead of concentration what we will use is the number of molecules N12. Okay. Then I will use a rate constant which I write as B12, the rate constant which I write as B12. But please remember this, I am not yet done. Why? Because absorption cannot occur spontaneously, right. What would it depend upon? It would depend upon the energy I am supplying it with, the electromagnetic field, right. So, what we say is we take this and we multiply it as a term which is rho nu. So, this is the energy density with which you are hitting your molecule, that is finally absorbing the energy you are hitting it with. Okay. Now, rho nu is your energy density, that is energy per unit volume over a per unit frequency interval or over a defined frequency range. Where have you seen this before? Rho nu, you have seen this before, tell me where. What was the first thing you did in quantum mechanics before you actually went on to the postulates? Yes, you did that, you did black body radiation. Remember, in black body radiation there was something known as rho nu, where rho nu d nu was equal to this times by over this times d nu, where you had this Planck's expressions coming in. So, rho nu essentially is this is exactly the same rho nu, it is your energy density. Okay. It is your energy density over a defined frequency interval or per unit frequency interval. So, rho nu is your energy density. So, that means what is your assumption? Your assumption is that means you are treating this whole process, as the molecule being a what? Black body emitter or absorber. Okay. So, that means your molecule is being treated as a black body system, that is what you are using it, it does not matter, because you know what the energy density is, you know the distribution, that is what you are using it for, right. So, this is equation number 1. Now, remember this was for the upgoing process, right, that is from 1 to 2. So, I should also have one rate equation which comes down the other way, right. So, that means if this is from the ground to the excited state, that means I am looking at an absorption process, what would happen if I want to come down, that is W21, that is the rate of coming down to the ground state from the excited state, that is from 2 to 1. This is equal to how many factors, how many terms would I be having here now? How many independent terms? In the first case, equation 1, I had only one term, right, which was n times b times rho nu. In the second case, how many would I be having, tell me? 2. I will be having 2. Why? Because I have two processes, one is a stimulated, one is a spontaneous, right. So, the stimulated, please understand, would just be the reverse of absorption. So, in this case what I would write is N21, there is a number of molecules in the excited state which is 2 times B21, that means the rate constant of this downward transition. Remember, I am talking about stimulated, and because this is stimulated, what extra should come along with it? Energy density, right, because absorption was also stimulated in the sense, right, you had to do that absorption. So, again you will be having the same rho nu. Okay. So, this is your stimulated. Lifetime is coming, lifetime will be coming from here, but lifetime is a result of that. Lifetime, this you will get the lifetime, hold on, right, lifetime will come from here, because we are talking about rates, right, and what is lifetime? Lifetime is the time it takes to decay, right. So, once we get the rate constant, we will get the lifetime too, simple. Okay. Then the next term has to be of your or for your spontaneous. So, it would be N21. Now, I define a new constant is A21, okay. N21 times A21, where A is a rate constant for what? Spontaneous transition or spontaneous emission down to the ground state. Now, tell me, along with this, should I write rho nu or not? I would not write rho nu, right, because this is not stimulated, this is spontaneous, right. So, that is why then this is your total expression for the rate of downward transition, and this is 2. Okay. Now, let us go to the next step. So, what we have seen is we have two different equations. In one case we have just one way of going up, in the other case we have two very general ways of coming down, right. One is a spontaneous, one is stimulated, right. One in which you do not have to hit, the other one which you have to stimulate, peg along to move down. So, suppose this happens. Suppose I say that there is no stimulating radiation. Suppose there is no stimulating radiation, that means it has absorbed, but for it to come back it does not get any stimulating radiation. That means for from 2 to 1 your rho nu is essentially what? 0. Okay. If that is the case, remember you have to have radiation for absorption to occur, right, otherwise it will not go up. But what I am saying now is once it goes up, everything comes down by spontaneous emission, there is no stimulated emission. So, then what I can write is, if this is the case, what I can say then d n to 1 over d of t, d n to 1 over d of t should be equal to now what should I write now here? What should I write? Minus n to 1 times a to 1, that is what you do, right. Rate constant times concentration, the same here is rate constant A times the number of molecules. So, this is 3. So, now what you can do is you can integrate this, So, you will be having d of n to 1 over n to 1 is equal to minus a to 1 d of t, and then you carry out the integration. Okay. Then you carry out the integration, it is very simple. So, what you will be getting is this, right. So, this is essentially what type of process, isn't it your characteristic first order process you are looking at. So, then what will happen is you can write n to 1 t is equal to n to 1 0, that means at 0 time e to the power minus a to 1 times t. Okay. That means at t is equal to 0, the number of molecules is n to 1 0, and then you are looking at its decay as a function of time, and it is an exponentially decaying function, right. So, let this be 4. Okay. Now, a to 1, what was a to 1? A to 1 was a rate constant, was not it? So, I can write this one again as n to 1 of t is equal to n to 1 0 e to the power minus t by tau to 1. So, now you can understand Pancham where your lifetime is coming, this is where it is coming, right. Okay. Do you know what this lifetime is known as, or this tau, what is it known as? See, we had encountered this tau before, that was the relaxation time and all these things before, right. But what is this tau known as? This tau, I will tell you what, this tau is known as radiative lifetime. Okay. This tau is known as radiative lifetime, that is why it is also referred to as tau radiative, and I can write tau radiative is equal to 1 by a to 1. This is number 6. Okay. Now, this is a very important equation where a is a to 1 is a rate constant for spontaneous emission from 2 to 1, that is from state 2 or level 2 to level 1. So, this way again this tau is called the radiative lifetime, and it is tau radiation, and this is actually the inverse of your rate constant for spontaneous emission. Okay. Good. Now, think about this. This is where we had considered there was no stimulating radiation to start with. Now, what happens if you have both? That means you also have spontaneous radiation occurring, you also have stimulated radiation occurring. That means, if both spontaneous and stimulated radiation occur, then at equilibrium, that means my equilibrium has been attained. If the equilibrium has been attained, then what will happen? The rate of upward transition would be equal to the rate of downward transition, right, and then I can write W12 is equal to W21, is not it? I can write W12 is equal to W21. Okay. So, from here then I can again write N12 B12 rho nu is equal to N21 B21 rho nu plus N21 A21. So, I have just put in the expressions for W12 and W21, that is what we had written before. Okay. What am I solving for? What I am solving for is rho nu, that means from here you find the expression for rho nu. So, then from here I can write rho nu N12 B12 minus N21 B21 is equal to N21 A21, or rho nu is equal to N21 times A21 over N12 B12 minus N21 B21, and let this be equation number 9. Okay. Let this be equation number 9. Okay. Now, please remember the assumption we had started with was rho nu is that of a black body. Rho nu is that of a black body. Okay. If rho nu is that of a black body, then what we can now do is we already have an expression for rho nu from Planck's hypothesis. So, we just use that expression for rho nu. If you remember that, from before, rho nu is equal to 8 pi nu cube, h nu cube over c cube times 1 over e to the power h nu over k t minus 1. This is what you know from before. See, essentially what you are trying to do is you have these rate constants B21 and A21, right. You have these rate constants B21 and A21. We have started with these, but we do not know what A21 and B21 are. We have to get expressions for these in terms of certain parameters we know, like say a Planck's constant, like a frequency, which is something very inherent when we are talking about spectroscopy, right. So, can we make a comparison between this one and the one we had already derived, which was equation number 9. Okay. But before going there, another assumption we will take is we assume that Boltzmann's distribution is maintained. So, we assume that Boltzmann's distribution is maintained. Okay. And if that is the case, then I can write n 2 over n 1 is equal to e to the power minus h nu over k t, e to the power minus h nu over k t. Here I am sure you have seen this, I can also write g 2 over g 1. Can you tell what g refers to? What does g refer to? Degeneracy, right. So, g refers to degeneracy. So, what this g 2 and g 1, they take care of the fact how many same energy levels you have of that specific level we are talking about, right. So, then from here I can write g is the respective degeneracy, right, and where 11 came from, please remember where 11 came from, it came from, if you would remember, if ever you would be doing this Boltzmann population n 2 over n 1, it would be e to the power minus h or e to the power minus e 2 minus e 1 over k t, remember. So, that is e 2 minus e 1 is what? So, delta E, which is equal to h nu, and that is what you are looking at. Okay. So, that is what your Boltzmann population is, right. So, that was number 11, right. Now, going back, so from equation 9, okay, let us go back to equation 9. From equation 9, what I can write is rho nu is equal to now I will do two small algebraic things. One is I will divide throughout, that is the numerator and the denominator, by n to 1. Okay. I will divide throughout by n to 1. So, what I can do is I can write a to 1 by n 1 to n to 1 times b 1 2 minus n to 1 will be cancelled actually, minus b to 1. This is number 12. So, I am dividing throughout by n to 1. Okay. Now, the next step is, see, I have to somehow get rid of the n's. Okay. I have to somehow get rid of the n's. One n I have already gotten rid of in terms in front of b to 1, that was I had divided throughout by n to 1. Now, what can I substitute in place of n 1 2 over n to 1? What can I do? Right, we just did that, right. So, here n 1 2 over n to 1 is essentially n 1 over n 2, because n 1 2 is the number of molecules in the ground state going to the excited state, and n 2 1 is the number of molecules in the excited state coming down to the ground state. Okay. So, then if we do that, so this is rho nu is equal to a to 1 over, so here if n 2 by n 1 was g 2 by g 1 e to the minus h nu over k t, what would this be? G 1 by g 2, then e to the power h nu over k t, right. Then I will be having b 1 2 minus b 2 1, right, let this be 13. Okay. So, here, so what I have done is we have used 11 in 12 to get 13. Okay. Now, tell me, you look at number 10 by yourself and look at equation number 13. What extra thing do we need to do to get a fair comparison between these two equations? So, look at the last factor of equation number 10. What is the last factor? 1 over e to the power h nu by k t minus 1. Okay. So, that means since it is minus 1, I should need to get rid of b 2 1 by putting a 1 out there. So, what do? I divide throughout by what? b 2 1. Okay. So, that means dividing 13 by b to 1, we get rho nu is equal to a to 1 over B21 because I have divided by B21 times 1 by what should I be having here now? I should be having B12 over B21, right, then G1 G2 e to the power h nu by k t minus 1. This is equation number 14 for me. See, is this okay? I have just put in 1 by dividing throughout by B21. Okay. Now what you do is compare 14 and 10. Compare 14 and 10. If you compare 14 and 10, what would you have? So, for example, in 14 or 10 has two factors. The first factor is 8 pi h nu cube over c cube, which should be equal to what? A21 over B21. The next factor is for 10 is 1 by e to the power h nu by k t minus 1. Okay. We already have minus 1, we already have e to the power h nu by k t, but what is the coefficient in terms of e to the power h nu by k t? 1. So, then comparing this, what can I write? So, I can write, so comparing 14 and 10, the first thing is B12 by B21 G1 over G2 should be equal to 1, or I can write G1 B21 is equal to G2 B12. That is one equation for me. This would be number 15. Now, let us look at the other fundamental one. The other where? G1 into B12. Why? It was G1 by G2, right? Tell me if I am wrong. It is G1 into B21, is not it? Or no? Why? No, B12 over B21 times G1 over G2 is equal to 1, is not it? So, then B12 times G2 right. क्या बोल रहे हो? My bad. चलो. B12 times G1 is equal to G2 times B21. This is what you are saying, right? B12 times G1 is equal to G2 times B21, right? Okay. So, that is one. Then the next thing is this. From the further comparison, we have A21 by what was the other one? By B21 is equal to 8 pi h nu cubed over c cubed. This is nu cubed over c cubed. Let me write it again. A21 over B21 is equal to 8 pi h nu cubed over c cubed. Okay. This would be 16. Okay. Now, look at the importance of this. Here what you are looking at is the ratio of two rate constants. A is the spontaneous rate constant, B is the stimulated one. 8 pi h over c cube is a constant, everything is constant. What is the variable? Nu cube. That means, the higher is your nu, which one would be more, spontaneous or stimulated? The higher is your nu, the more would be your spontaneous transition, right. So, that means higher nu leads to more spontaneous transition. Okay. Now, pause a little bit and think about this. Lasers, it is light amplification by stimulated emission or radiation. I have to have stimulated emission. what is the competing process with stimulated emission? Spontaneous emission, right? I would not like to have too much of spontaneous emission when I am talking about lasers, and I will tell you why. Okay? Try to understand this. In lasers, see, if you are stimulating something, that means if you have a certain electromagnetic field with a certain phase coming in, and that radiation is stimulating the downward transition of a molecule from the excited state to the ground state, what will happen is when it will interact, it will keep the same phase information. Okay? The phase information would be the same, right? This leads to something known as coherence in light. So, what do you mean by coherence? Coherence means everything kind of is moving along in the same direction, maintaining the same phase relationship, because if they move out of phase, what will happen? They would destructively interfere with each other. So, that means you will always have to maintain the same phase. Okay? That is where it comes from. To give you a very simple example, a real life, if you would ever see soldiers marching on a bridge, you would see they always lift their legs together in coherence. That is in coherence. That means they are not running out of phase, and it really looks beautiful when they do the drill, because each and every one is marching simultaneously, synchronously, actually that is the word, by lifting that respective leg or bringing the other respective leg down simultaneously. So, if one is lifting the right leg, everyone else lifts the right leg. That is a coherence. That means if you are hitting or stimulating radiation at a certain phase, then the ones which it stimulates to come down will also be coming out in the same phase. Now, this gives rise to something known as coherence, which it is called a coherent property of light. But think about spontaneous. In spontaneous, there is nothing, right? In spontaneous, because spontaneous is nothing, the photons or the molecules can come down in any way, maintaining any phase relationship. That means the light coming out can have any phase relationship. So, that is called non-coherent radiation. Lasers is always about coherent radiance, because you need a very focused light with high intensity beam, right. So, laser radiation is always coherent, right. So, that means to have a coherent laser radiation, I would have to have the least amount of spontaneous radiation possible and the highest amount of stimulated radiation possible. Okay. Now, you look this up and you come back and tell me, but I will give you something to think about. It is very hard to find lasers in the blue, especially in the UV. Can you tell me why? Right. So, think about this. Whatever lasers you see, you know, there are diode lasers and all these things nowadays, it would be mostly like 400 up and so. The moment you come to the UV, what will happen is the nu is very high. Now, because the nu is very high, what is happening? The ratio is increasing, that is, the spontaneous emission is becoming more. If the spontaneous emission is becoming more, then the efficiency of the laser is going down like anything. That is why it is very hard to get lasers in the blue, in the UV, and if you are going to get one, it becomes really expensive, just because of this simple principle. Remember, because this is a fundamental nature of your light, you cannot do anything with it. The only thing you can do is devise some method to counter it, but there is no other way you can do it, because this is what you have just derived without any principle, right. It is just based on equilibrium. So, please remember this. The amount of stimulated or the amount of spontaneous emission you have, or the ratio of the stimulated and spontaneous emission, is governed by the nu cubed. That is why you go higher up, you go visible and all these things, where the nu becomes lower and lower, what will happen is you will see more and more lasers coming up. Okay, that is typically why it is. Again, take it from me, this is a very fundamental thing you ought to know. It is a very fundamental thing, and that is why Einstein's A and B coefficients are so important in spectroscopy, absorption and fluorescence, right. Einstein's A and B coefficients, especially the ratio of A over B, because it tells you exactly in which region you are not going to get a very efficient laser system, because your stimulated emission is going to decrease drastically, rather your spontaneous emission increases like anything. Okay, will you keep that in mind? Good. So then these Einstein's A and B coefficients have also other meanings. I will come to those when we deal with those things later, as and when we deal with those things, right. Now, before ending this class, I will just introduce something with which I can carry on in the next class. So, let us go back to the slides. Let us talk about a transition. Okay, let us talk about transition. Now, what do you see here? What do you see here? So, on the y axis you have energy, potential energy. On the x axis you have R. What is R? No, reaction coordinate, it is not the reaction coordinate here. Well, it is a reaction coordinate, but it is a bond distance, it is the internuclear distance, right. Where have you seen this before? What feature of quantum mechanics does this come across? Frank quantum principle, excellent, it comes across in Frank quantum principle, right. Okay. So, what here you have one of the very simple pictures. What you have is you have two states, one is the ground state which is S0. What does S stand for? S stands for singlet, you can see the electrons are paired, right. Then in the excited state you also have another singlet which is S1. So, 0 is the ground state, 1 is the excited state, right. And what you will be doing is, if you would be sending in enough radiation, then the molecule or radiation of the current frequency, of the correct frequency, the molecule would absorb, and then it would make a transition to the upper state. Okay. Now, before going deeper, see, there has to be something which determines this, right, which determines the intensity of your transition, the probability of your transition, and all these things. Okay. Now, that is why Frank quantum is so important. Now, look at this. Why did I draw a vertical arrow? I could have drawn an arrow which was like this. What is the difference between me drawing a vertical arrow and me drawing a slanted arrow? What happens? No, tell me what happens. I know that. Tell me what is the difference between a vertical transition and a sloping transition. Just refine what you said and tell me what do you mean by vertical transition. What is not changing when you make a vertical transition? R is not changing, right? That is what you said, but I just want to know the answer. R is not changing. If I do a sloping transition, what happens? You can see R is changing, right. Now, Frank quantum said that each and every transition has to be what? Vertical. And why does it have to be vertical? Because, as you said, nuclei are much more massive than electrons, right. That is why this is a vertical transition. You cannot have a transition which goes like this. You cannot have a transition which goes like this, right. Second, you look at the two states S0 and S1, right. What are these levels? What are these levels? You know, these levels, what are these levels? Okay, very good. So, these are vibration states, right. So, that means in S0 you are looking at an electronic state along with vibration energy levels. In S1 you are looking at electronic state along with vibration energy levels, right. Now, remember your psi, your total wave function is or should be having electronic component, vibrational component which is the nuclear, and there is one more. What is that? Rotation. Then in between the vibration energy levels you will also be having what? Rotation. Okay. But we will not worry about rotation that much here. Two principal things we are going to worry about, one is electronic and one is vibration. Okay. Second, guys, how do you think, or tell me, if you would be drawing this curve, okay, if you would be drawing this curve, how would you draw this curve? This is actually a Born-Oppenheimer approximation. This curve actually tells you what a Born-Oppenheimer approximation is. Tell me, how would you draw this curve? What does Born-Oppenheimer approximation say? It says that essentially these two motions are independent of each other. The electron moves much faster than the nucleus. Okay. Do you remember in Born-Oppenheimer approximation you said something that the electronic wave function has a parametric dependence on the nuclear coordinates? Do you remember that word, parametric dependence? See, what happens is, it is very simple. The nuclear also vibrating, right? Okay. Whether it is in the same state or whether you go to a different state, the internuclear distance can change. See, for example, in these two curves, the ground equilibrium distance for this one was r e say prime. For the excited state, it is r e double prime. Now, has the equilibrium internuclear distance changed or not? It has changed, right, because you can see the upper state is shifted slightly to the right as compared to the lower state, and because the minimum occurs at what? The equilibrium bond distance. What you can say is that once you have excited the molecule, what has happened? The bond length has increased, isn't it? The bond length has increased. Tell me a typical situation. Suppose I give you a molecule which is ethene. It has a sigma bond and a pi bond. Okay, it has a certain bond length. Now, we hit it with a radiation where what happens? One of the pi electrons goes to into the what orbital? From the bonding to the antibonding molecular orbital. If it goes to the antibonding molecular orbital, what happens to the bond order now? Initially it was 2, now it is 1, right. Now it is 1 because one of the electrons is already in the antibonding orbital. So, what has happened? The bond order has changed, decreased. So, what will happen to the internuclear distance? Increase. So, this is possibly one of those situations, right, where the internuclear distance increases, right. It is one of the cases. Okay. Now, what does the parametric dependence come from? So, look at this. Because the nuclei cannot move as fast as the electrons, but remember, even when you are making the transition, the molecule is still vibrating. It is only that you have decoupled these two. That means, it is called a separation of variables in that sense, which you do in 2D and 3D harmonic oscillators or particle inner boxes. So, parametric dependence means is what you do is you take a certain R, okay? You take a certain R and solve the Schrodinger equation at that R. So, you will be getting, since you are solving for psi electronic, you will be getting E electronic, that means energy of the electronic state at that value of R. Okay. Now, again you change R. So, for example, what you are starting is you look at this R, this R. So, this is say R1. R1, at R1 what has happened? At R1 there is almost no attractive force between these two, that is where it has tailed off. Now, what you are doing is you are keeping the nuclei fixed at R1, and now you are solving what is Schrodinger equation. So, you get E electronic, right, then you plot E1 out here. Okay. Now, what you do is you change R1, so you go to say R2. Once you go to R2, again you solve for E. So, then say you get E2, and you go on doing that. Once you go on doing that, what will you get, right? See, because you cannot take these two things together. The thing that helps you is the electrons are moving much faster than the nucleus. So, if you are assuming that the nucleus has changed, the electrons are bound to follow that. Okay. So, what you are saying is that I fix the nuclear positions at different R's, and then I solve for the electronic energy E electronic, and then I plot that. Once you plot that, this is the curve you get, and this is your Born-Oppenheimer approximation. This plot tells you the Born-Oppenheimer approximation. This is how you get it. Okay, that is the signature of this plot. So, Born-Oppenheimer approximation, that is how you would plot it, and this is called a parametric dependence. That is why you will see, if you are looking at psi total, it is given as psi electronic, then it says R comma R, then psi nuclear, or I can write vibrational R. So, this is your psi. I will come to this in the next class, but just realize the importance of this. This psi electronic, how many coordinates does it depend upon? What are the two coordinates? One is R, small r, and the other one is big R. What is small r? Small r is the distance between the electrons, is interelectronic distance, right, or it is the distance of the electron from the nucleus. Okay. So, So, it is a position of the electron. What is big R? Big R is the distance between the nuclei. So, that means your electronic wave function is not only dependent upon the position of the electrons, but what is it also dependent upon? The position of the nuclei. And when you draw a plot like this is what you get out of it. Okay? This is essentially what your Born-Oppenheimer approximation is. Psi vibrational essentially just depends upon the distance between the nuclei. Okay? So, remember, each and every plot like this is actually a picture of your Born-Oppenheimer's approximation. That is how you get it. Okay? So, this is where we start with some of the very essentials of spectroscopy, and next class we will go into Frank-Condon factor or Frank-Condon overlap. That is what determines the intensity of the transition, all these things. Okay.